Good morning. Welcome to NPTEL course Transfer Phenomena in Bioprocess Engineering week 3. So, last class we discussed about the different type of friction factors, whether laminar flow or turbulent flow, this one. But this class we will discuss more on the Bernoulli equation, that is very important for the bioprocess here. So, why you want to study the Bernoulli equation here? So, the many bioprocess engineering systems, especially here the many bioprocess engineering involve fluid flow, example fermenters, then pipelines, then heat exchangers, pumps, membrane systems, water treatment plants, everywhere we will use for Bernoulli equation. So, engineers frequently need to determine the fluid velocity. The velocity is very important. Then the pressure changes, what the pressure changes here, then the pump requirements, so then energy losses also. In such a cases, the Bernoulli equation provides a powerful tool to analyze these systems. For example, for industrial fermentation tank, the culture medium needs to be pumped from storage tank to bioreactor. So, then we need more thorough knowledge about the Bernoulli equation. So, then what are the question here? What pressure is required to pump that one? So, how much energy does the pump need here? What is the velocity will the fluid achieve here? So, these questions only can be answered if you use the Bernoulli equation. So, using a Bernoulli equation. So, we need Bernoulli equation for thoroughly to study here. So, the conservation of energy is a famous, this first law of thermodynamics is there. So, energy can neither be created nor destroyed, but it can be only transformed from one form to another energy. So, for flowing fluids here, the total energy at point 1 equal to total energy at point 2. If one, you can add some energy, but provided no energy is added or lost here. So, what type of different forms of energy here? So, there is a pressure energy due to fluid pressure, then kinetic energy due to the velocity, the fluid velocity here. Then what is the potential energy due to the elevation, because the potential energy because of height the potential energy will be there, but kinetic energy there is a velocity, wherever velocity is there then kinetic energy involved here. The pressure energy, wherever the fluid pressure is there then the form as a pressure energy. So, basically you had all three type of energy here. So, the Bernoulli equation here state that the sum of all the forms of energy, the fluid flowing the enclosed path is the same at 2 points in the path. So, here the assumption here flow is a steady state, because so many times we discussed what is the steady state. Steady states do not change with the time, that is called a steady state. Steady state normally do not change with the time, that is the meaning. If unsteady state, you add here again unsteady state, then it will be a definitely change with the time, not don't, it is a change with the time. Unsteady state whenever there, then we have to use lot of accumulation, but normally in unsteady state solving is a very tough for this one. But normal steady state we can use very simple and we can solve it, but whenever go to unsteady state, when we have to use an ordinary differential equation and even you have to use MATLAB solver, different solver, all this there. So, density is constant, we assume as an incompressible fluid, so that the life is very easy or is very difficult to solve. So, the density is a constant. Then the friction losses are negligible, of course some losses should be there, but for assumptions there is a friction losses are negligible, no energy losses due to viscosity. So, here the first is the pressure one P1, you can see here what is the pressure 1, the corresponding A1, and then what is the height of this one, you assume this is the height. The height 1 is h1, then from here to here the v1 is the velocity, then velocity is the meter per second, then delta t is a time second, get cancelled, that we will get how much distance of that one. So, this is a v1, same way it is moving to another of this one, it is called a P2 pressure 2, there is a area A2, then the height is here, that height is a h2, then somewhere some velocity is there, that is a v2. So, we need S2, that is a multiplication of V2 and delta T, we will get S2. So, consider the fluid moving from point 1 to point 2, the energy in equal to energy out. If you say add these both together, the delta energy should be a 0. So, here 3 types of energy is there. One is the pressure force, then another is the kinetic energy, then potential energy. All 3 together it gives us a 0. So, here pressure force, what is the pressure force here? Fs here, we call as a Fs. Then kinetic energy of me square, because here kinetic energy, the velocity play main role. Then potential energy, the potential energy height play main role, mgh, the height is the very main important here. So, the pressure force F1 S1, we can write F equal to P into A. Of course, P equal to pressure equal to force by unit area. So, P1 A1, the S1 we can write a V1 delta T. V1 is the velocity. So, meter per second, then here also second we will get, then V1 we get directly in terms of S, how much is moved that one. So, same equation you make a numerator denominator divided by density. So, then you can rearrange the equation, the A1 V1, then density here, then the P1 delta T separately here. So, the rho you can write the rho here m dot, that is the m dot is the mass flow rate here, then the P1 delta T here. So, this is a normally the continuity equation, the rho 1 A B we can write always continuity equation m. I think you already discussed here, that is a continuity equation of m mass flow rate equal to rho A V. So, rho A V, density, area, velocity, we always write a m dot mass flow rate. So, m dot is here P1 delta T, then the rho is here, then again this m dot we can write, that is a mass flow rate, then we can write m by delta T. That is only we are writing the m dot equal to, we can write m by delta T. Here we are writing m by delta T. So, the delta T cancel, then we can write m P1 by rho. The first one is for m P1 by rho. The F1 S1 for pressure forces we can write like this. So, the Bernoulli equation here you assume like two place this one, the point number 1 and point number 2. The first one is the F1 S1, then other one is for of me1 square, that is the kinetic energy, mgh1 is the potential energy, this is called as the potential energy at point 1 or location 1. So, same way for 2 we called as the F2 S2, then of me2 square, that is the velocity of this one, then h2 here potential energy. So, this F1 S1 we can replace m of P1 by rho, then of me square, whatever this one, same way m of P2 rho, because just now we discussed now how we are getting that one. So, then this all equation you make divided by m, then we will get a here P1 by rho, the P1 by rho of V1 square kinetic energy, then GH1 is the potential energy, point 1. So, same way point 2 we will get the same way P2 by rho 1 by 2 V2 square GH2. So, this is another form of equation, we can write P by rho and V square by 2 GH equal to constant. This is a Bernoulli equation for the this one. Normally we use for the pipeline systems. So, here Bernoulli son the continuity equation already we discussed, m dot equal to rho 1 V1 A1, that is a mass flow rate here. So, most of the practical problems again both equation, that is a continuity equation, what we discussed is a continuity equation, the Bernoulli equation for energy balance. Together they solve the pressure and velocity simultaneously. So, what are the application for this one? When normally used for orifice meter, the measure the flow rate of fluid flowing through a pipeline we will use for orifice meter. Same way for Venturi meter also, the flow measuring device is consisting as a thin metal of plate with a circular hole, that is the orifice here installed in the inside of pipe. So, flow in pump everywhere we will use for Bernoulli equation for bio problems, and in the orifice meter, Venturi meter, all type of measuring device we will use this one. So, now initially we assume as there is no fluid friction. So, now what will happen if fluid friction is there? So, fluid friction is defined as the conversion of mechanical energy into heat in a flow stream. Whatever energy it converts into a heat of this one. So, it is normally we denote like HF, the friction of this one, HF equal to joule per kg, joule per kg. The HF represents the friction generated per unit mass of bed. So, the Bernoulli equation becomes, now we are modifying the equation. This equation know at point number 1 and this equation you know at point number 2, we are adding the friction HF here, additionally we are adding the HF. So, then this called as a with friction, what is the Bernoulli equation here. So, even if you want here, we can add even efficiency of pump also, it of efficiency into work done by pump. We can add it here, we will get a one more equation, so that we can modify, we can keep on modify here. The first one is very simple form, and here we added the eta WP, the efficiency and then work done by a pump, both we added. Then here friction also added here. So, this is overall the Bernoulli equation, how to use for when the friction occurs, when the pump efficiency if it is there, then how to use here. So, we will see simple problems. So, here you read this one, the fluid density 960 kg per meter cube, the density is the rho value is 960 kg per meter cube, is flowing steadily through a tube as shown the figure. The section diameter or D1 equal to 100 millimeter, this one D1. Okay, and because this is a point number 1 we consider here, and another is a point 2, and the D2 is the 80 millimeter, DT is 80 millimeter. So, the pressure is already available 200 kilonewton per meter square. So, then the velocity also U1 equal to 5 meter per second given. The tube is horizontal. If it is tube is vertical somewhere or some height is there, so automatically the potential energy involves. Whenever the tube is horizontal, then the potential energy is 0, because the potential energy rate for rho g H1 equal to rho g H2, because H1 equal to H2 both are same. So, then we will get both will get cancelled, then only the potential energy is automatically will get 0 if it tube is horizontal. So, what is the pressure at section 2? So, values are given 960, then the diameter of this 0.1 meter is there, the diameter of section 0.08 meter is there, pressure is there, velocity also available, velocity only they gave the first point 5 meter per second, not the second one. So, the pipe orientation horizontal, that means that automatically the potential energy here, this will be a 0 automatically. If it potential energy, if it horizontal pipe automatically get 0, because both H1 H2 are same. So, then automatically the values are same, G also same, get cancelled one. So, for incompressible flow, this is a mass of continuity equation, we know already rho 1 A1 V1, rho 2 A2, since both density same. So, only A1 V1, A2 V2. So, A1 is again area we can write pi D1 square if it uses a circular pipe. So, diameter already given the value, the problem diameter 0.1 meter is there, use that one, get the value of A1. Same way use here, get the value of A2. So, both A1 and A2 done at area at section 1 and section 2. Then the continuity equation here A1 V1 equal to A2 V2, from there V1 already know the value, because V1 already given the problem itself. So, the velocity at the 5 meter V1. So, we can calculate directly V2, the V2 velocity is here 7.8 meter per second, 7.8 meter per second the V2 velocity at point 2. So, now V1 we know, V2 we know. So, there is a, you have to use a Bernoulli equation for steady, this is steady, and incompressible fluids, then frictionless flow. If it frictionless is there, friction is there, we have to add a HF here. Since the pipe is horizontal, automatically Z1 Z2 both are 0, because pipe is horizontal, this both will get a 0. Then we modify this equation like this, because the horizontal, then potential energy automatically 0. So, then multiply this one, and you, after modification we know the value of P1 value, and then V1 V2 we know. So, from there you just use this one, then we can get from here P2, the pressure of 2. The pressure 1 is first, the P1 is 200 kilopascal, but the pressure 2 is a 182.7 kilopascal, but the pressure decreases as a fluid enters in the small diameter, because here is coming as a 200 kilopascal at entry point, but the final point is 182.7 kilopascal. It looks the pressure get a decrease here. So, next problem 2 we will see. So, water flows steadily through the pipe shown figure such that the pressure at section 1, this is a, I think here they are considering this as section 1, okay, not here, it is a pressure 1, section 1 and 2 are 300 kilopascal and 100 kilopascal. So, here this is a P2, so 100 kilopascal, then pressure 1 is a 300 kilopascal respectively. Determine the diameter of pipe section 2, and the section 2 here they are asking what is the D2 value, but the D1 is here, the velocity V1 also there, the V1 is 20 meter per second, velocity also there, but the viscous effects are negligible. So, P1, P2 already given and velocity we know V1, but V2 we do not know, and D1, Z1, Z2 all we know because the height is there, height difference is here, Z1, Z2. Then the density is the 1000 kg per meter cube, okay, because height itself given here, the value is the 50 meter, the 50 meter here, the value is already given, maybe here you are not able to see that the 50 meter here. So, now we have to use the Bernoulli equation. Bernoulli equation is a very simple, the B1 by rho, V1 square, GZ1 by this one, Bernoulli equation. So, pressure term P1 by rho, P1 we know that 1000 is a kg per meter cube, then we get a P1 by rho, this value done. Then P2 also already given value 100 kilopascal. So, then P2 by rho, this is also done. So, we know P1, P2. Then next is for velocity, because velocity we know, V1 we do not know, velocity 2 we know, velocity 2 we know, that is why velocity 2 they are keeping here and getting the value of V1. So, once V1 done, then Z1 we know, see Z2 is a 0, because Z1 is a 50 meter height, the height is a 50 meter height. So, we can use only here the 50 meter height, because the problem itself already given, the sections are here, yeah 50 meter here, 50 meters there. So, the 50 meter we added here, Z1, Z2 0. Once this done, you substitute all the value and get the value of velocity, because all value just substitute inside, then V2 square will get it, V2 is a 42.2 meter per second. So, for incompressible flow, we always use the A1 V1 equal to A2 V2 for the continuity equation. So, now area at section 1, what is the area at section 1? A1 pi D1 square, pi D1 already available, calculate the value. So, A2 equal to, because they are using rho 1 A1 V1 equal to rho 2 A2 V2, this is called continuity equation. So, from there we can calculate A2, the A2 values of this value. So, A1 already is there, A2 is there. If you know A2, from there we can calculate the D2, because they are asking the end of the problem, what is the D2 diameter of this one. So, from there we can calculate, because the problem itself you can see here, they are saying that determine the diameter of pipe at section 2, section 2 here they are asking, okay, what is the diameter of pipe at section 2. So, we can calculate from here. So, finally we got this one, so diameter of pipe is a 0.068 meter at section 2. So, if you want to continue, if you want to check also, verify also, we can use and verify whether we are getting the same value or not. So, that we will get some idea, the rho 1 A1 equal to rho 2 V2, rho 2 A2 V2 both are same. So, next is the problem 3. Here a fluid density of 1.7 gram per, the density rho value 1.75, then viscosity here 8.1 centipoise. It flows in the pipe of variable circular cross section as shown figure. This is a figure shown here. The flow rate into the pipe is, the flow rate pipe Q value they given 0.053 feet cube per second. This is a Q value. Then they are asking what is the average velocity in feet per second of the fluid at the exit. When they go outside, what is the velocity here? So, volumetric fluid already given, inlet diameter 2 inch, then middle diameter 2 inch, the middle diameter is a 6 inch, then outlet is a 4 inch here, 4 inch. Then the density is already given 1.75 here, density also there, then viscosity also here. So, we know all the values, but what they are asking here, what is the average velocity? They are asking of the fluid V2. V2 they are asking what is the V2. Okay. So, we can calculate from here. So, Q equal to we know V velocity Q by A, then the D exit we know 4 inch already mentioned. You convert it in terms of feet, because area already in terms of inch, then convert in terms of feet. Then you substitute in the square, then we get a area here. Once the area we know, then we know the Q value also. Q value is already given here. The Q value here, the flow rate is there. Volumetric flow rate 0.053 feet cubes per second. So, already Q values are there. You just use the Q value and A value, from there we can get the velocity. The velocity here V equal to 0.607 feet per second. So, that is the total final velocity of this one. So, the problem 4, it's the last problem, we will see here. The water flows at the rate of 0.4 meter cube minutes, that is again is a Q, this is a volumetric flow rate. But normally mass flow rate, then what you have to do? Mass flow rate, you have to convert mass flow rate kg per second. Here volumetric flow rate meter cube per second, we can convert from volumetric flow rate to mass flow rate. But what we have to do here meter cube per second, and then you want to kg per second. So, very simple. This is a mass flow rate we need here. You multiply with the kg per meter cube. Yeah, you can multiply. I think the previous class something I said, it's a divided, it should be a multiply. So, meter cube per, yeah, it's a meter cube per second, and this is a kg per meter cube, both will get cancelled, then kg per second will be there. So, kg per second, that is a, we will get a mass flow rate, that the water flows at the Q value at 7 centimeter diameter of pipe, at pressure is 70 kilopascal, the pressure is a 70 kilopascal, pressure is 70 kilopascal. If the pipe is reduced to 5 centimeter diameter, the reduce the 5 centimeter diameter, the pipe is 5 centimeter diameter, calculate the new pressure in the pipe. So, they are asking what is the new pressure in the pipe. The density of water is 1000 kg per meter cube, then the flow rate is the 0.4 is there. So, flow rate is a volumetric flow rate. So, volumetric flow rate here, and the D1 is 7.5 centimeter, the first one, then D2 6 inch is there, then okay, the pressure P1, the rho is a 1.75 gram per centimeter cube. So, determine the velocity at section V1, V2 they are asking at pressure section. So, we are asking V1, V2, then P2, all three we have to find here. So, you know Q value, Q equal to 0.4, that is Q equal to 0.4, but you convert in terms of seconds, because the problem already given 0.4 meter cube per minutes. So, you have to convert in terms of meter cube per second. So, once this is done, that Q value is done, Q equal to this value. At area section D1, D1 is already available, I think already is there, 7.5 centimeters there. So, once D1 we know, we can calculate area A1. So, A1 once you done, A1 finally we got this value, A1 equal to, because A1 equal to pi D1 square by 4. So, once it done, then we can calculate velocity, velocity equal to Q by A, because Q value already we got it from here, the Q value from here we got it from problem already given in terms of minutes, we convert in terms of second. So, finally, we got the V1 value, the velocity at 0.1 we got a 1.509 meter per second. Again same way calculate area section at 2, but the diameter they mentioned 5 centimeter, then we convert in terms of meter SI units. So, we calculate A2, then we got new A2 is here, this is the value. So, once A2 we know, then we can calculate from here V2, because once we know okay A2 V by QA2, from there we can get a V2 value. So, once the Vt is there, then use the continuity equation, we get V1 equal to in terms of function of V2, because we know V1, we know V2. So, just put all this one, then we get in terms of some multiplication of this much amount is called as V1. So, V1 here, V1 equal to 0.44 of V2, the summation of this one. So, now horizontal pipe you have to see, then P1 by rho, because this is I think this is a horizontal pipe. So, then there is no there is no the elevation here. If there is no elevation, then automatically the potential energy become a 0. So, we are using only here U1, yeah, this is already Z1 to Z2 both are same. So, automatically the potential energy is 0. So, only we have to calculate only this one. So, you rearrange the equation, then you substitute V1 square, V1 equal to 1 point, already there 1.509, then V2 also here, V2 value, use this value and then make a difference of this one. So, we will get the finally P2 equal to this one at pressure section at 2 here. So, finally, the P2 equal to 65,375 Pascal. So, sometime we can write in terms of other Newton per meter square or different units are here. The final solution here, the velocity here 1.51 meter per second, V2 3.4 meter per second, the V2 we got as 65.4 kilopascal. So, this problem little it is very easy, it is not very tough here, but only you have to use this the volumetric fluid in terms of mass flow rate converter one, like that you have to lead some, okay, then we have to submit the Bernoulli equation. The Bernoulli equation here, the Bernoulli simple Bernoulli equation, we can add it here rho g H1 and rho g H2 plus, and here if you add it sometime what will happen, the efficiency of the pump we can add in this spot F eta Wp, but here we have to add a HF friction loss if friction head is there. So, we can add it here. So, after solving this one V1 we know, V2 once V1 V2 know, you know the P2 value, P2 also we can calculate from here. So, finally, we are able to calculate all values. Thank you.